Hello, it's Mr. Neil, and in this video I'm going to review the Database Design and Development Unit from Higher Computing Science. In this unit you need to analyse and design solutions to database problems. Then, utilising SQL, you need to implement a number of SQL queries and test them and evaluate them to ensure that they're accurate and fit for purpose. You can find the full unit specification for database design and development within the Higher Computing Science course specification, which is available on the SQA website. Starting with analysis. The end users are the people who are going to be using the database. Their requirements are the tasks that they expect to be able to do when using the database. We can then take those end user requirements and develop the functional requirements. These are the processes and activities that our database has to perform. The functional requirements will also specify the information that the database has to contain in order for it to function. For example, a travel agent that stores details of bookings for hotels in Scotland. Staff at the travel agency may wish for the database to show the available hotels with specified features, for example, swimming pools, golf courses, and those that are all inclusive. So therefore, based on this end user requirement, the database will need to store information about the features that the hotel has. By identifying the requirements at this stage, it helps clarify what the database should do, identifying the features that we need to implement, and then we can later use these requirements to evaluate the system to see if it's fit for purpose. Moving now on to design. From National 5, you will recall the terms entities and attributes. An entity is something that we store data about, a person or a thing. An attribute is the information that we hold about each entity. You as a student at your school are an entity, and your school will store information about you, your name, your address, your date of birth. At both Higher and National 5, our databases will include a number of entities. And between those entities, there will be relationships. And we can describe these relationships as the cardinality between entities. Cardinality can be described in three ways. Let's look at an example to explain it. One head teacher traditionally leads one school, and one school is led by one head teacher. This is a one-to-one relationship. One school has many students, and one student attends one school. This is a one-to-many relationship. One student studies many subjects, and one subject is studied by many students. This is a many-to-many relationship. When we come to implement our database, many-to-many relationships cannot be implemented. So instead of one many-to-many relationship, we would then add an additional entity and use two one-to-many relationships, and I've got an example of that shortly. Whilst it may be possible to identify the relationship between two entities straight away, we can use an entity occurrence diagram to help us. An entity occurrence diagram illustrates the relationship between the instance of one entity with the instances within the related entity. An instance of an entity is one specific example of an entity. These will become the records within the table during implementation. In an entity occurrence diagram, each entity is shown in a tall oval. Inside the entity, each instance is represented by the value of the primary key, and each relationship is illustrated by drawing a line to the associated instance. For example, head teacher 84 is the head teacher of school IC57, and students 77, 123 and 295 all attend the school IC57, which is led by the head teacher 84. You should be familiar from National 5 with entity relationship diagrams. An entity relationship diagram is a graphic representation of the entities within a database. It is used to illustrate the relationship that exists between entities. An entity relationship diagram should show the name of each entity within the database, the name of the relationship between two entities, the cardinality of the relationship between two entities, and if required, the name of each attribute within the entity. In our example here, the cardinality is represented with a line through the relationship to denote one, and then the crow's foot to denote many. We've also described the relationship between each entity. Earlier I said that many-to-many relationships were not possible, and we had a many-to-many relationship between student and subjects. To break up this relationship, we can add in a third entity and have two one-to-many relationships. Let's now examine the content of the choice table. You can see here we're pulling in the student ID from the student table and the subject ref from the subject table, and we have another attribute called level. Now, how do we identify each record within this table? Well, we could add another attribute that would be our primary key, or we can make use of something called a compound key. A compound key is a primary key that comprises of two or more attributes. Each attribute that makes up a compound key is a primary key in its own right. So in our example here, our compound key can be student ID and subject ref, as both of these are primary keys within their respective tables. Data dictionaries are created during the design phase to define the structure of a database. Data dictionaries contain data about the data that will be in our database. It identifies the name of each entity and the attributes within those entities, the type of data that will be held in each attribute and the size of that data, an indication of any primary and foreign keys, and any validation that rules that will be applied to the attributes. Here's an example of a data dictionary. From National 5, you will recall that a database can store text, number, date, time, and boolean. We can also apply a range of validation to the different attributes within our database. A presence check to make sure there's a value entered into the field, a field length check to restrict the number of characters that can be typed in, a range check to ensure that the data is within certain limits, and a restricted choice to limit the number of options that the user can select. It's important to take time to design any queries that we may need to implement later. Planning ahead will help reduce the amount of frustration that you may encounter when working with SQL code. Query design does not need to include specific SQL, it is merely an indication of what we want a query to achieve. The query design should include any fields, including calculated values and aggregate functions, the tables needed, any search criteria, what groupings are needed if required, and the sort order. Let's now look at implementation. The majority of the implementation at Hire is relating to SQL. Starting with wildcards. A wild character is used as a substitute for no, one, or many characters in a string. There are two different wildcard characters. The percentage sign represents 0, 1, or multiple characters, and the underscore represents one single character. If you use Microsoft Access, the wildcard characters are asterisk and question mark, instead of the percentage and underscore characters respectively. Where surname, like Mac percentage, will find any surname that starts with Mac. Where surname, like percentage 0, will find any surname that ends with the letter O. Where surname underscore H percentage will find any surnames that have H in the second position. Calculated values are values that do not exist in a table, but are created in the select statement. Aliases are created to make columns selected by SQL statements more readable by giving them a temporary name. So in this example here, first name has been given the alias student name. And we have a calculated field here that will add the coursework and the exam mark, and we have an alias for it called total mark. Aggregate functions are used to calculate values from the data in columns, and are often used with the group by clause to provide calculations on groups of records in a column, and we'll talk about group by in a second. There are 5 different aggregate functions. Average returns the average value on a numerical column. Count returns the number of rows that match the criteria in the where. Max returns the largest value, and minimum returns the smallest value, and sum returns the total sum of a numerical column. Group by, as previously mentioned, is an SQL keyword that can be used to group a set of records in a query by some given criteria. It gathers any data that is identical in the field we want to group by. In this example, we are grouping students into their class and then ordering them in alphabetical order. It is important to remember that group by comes before ordered by. If we were then to execute that query, we'd get the results here. And as you can see, all students in the same class are grouped together, and our classes are in alphabetical order. When testing queries, it is a good idea to document expected results and actual results. Comparisons can be then made with testing passed if the expected result and actual results are the same. Queries should be evaluated for the accuracy of their output. Results of test runs can be used to judge if the database provides accurate output for the functions identified at the analysis stage. A database is deemed to be fit for purpose if it meets the requirements determined at the analysis stage. In this video, I reviewed the Database Design and Development unit from Higher Computing Science. If there are any aspects of this unit that you're not sure of, I'd recommend that you undertake further revision. There are loads of resources available to support you with your revision. These could be resources from your own classroom teacher, or those available on the SQA, BBC Bitesize, or Scholar websites.